You've been told for years that our galaxy is on a fixed crash course, that the Milky Way and the Andromeda Galaxy are already scheduled to smash together in a few billion years, no questions asked. It sounds final and scary, but here's the tension at the heart of this story. The part most people never hear, that certain collision was never as certain as it was sold to you. In 2012, a high-profile study using the Hubble Space Telescope pushed this idea into the spotlight. NASA put out statements, videos, and press material, all repeating the same line in simple language. The Milky Way and Andromeda will merge. The first close encounter in about 4 billion years, the final blended galaxy a couple of billion years later. It was presented less like a scientific scenario and more like a fixed appointment far in the future. The phrase that stuck was that the future collision was certain, not just likely, not just the most probable option, but treated almost like a guarantee. That word matters, because when an agency like NASA uses it, you tend to file it in your brain as fact, not as this is our best guess based on the data we have right now. The story spread fast through documentaries, science channels, textbooks, and infographics, and the idea of an inevitable Milky Way Andromeda smash-up became the standard explanation. Before we question that story, you need the basic numbers that supported it, because they are still real and important. Andromeda is about 780 kiloparsecs away from us. In more familiar units, that's roughly 2.5 million light-years, or about 15 quintillion kilometers, which is around 9 quintillion miles. The light you see from Andromeda left that galaxy about 2.5 million years ago, so how fast is it moving? Along the line that connects us to Andromeda, it is coming towards us at about 110 kilometers per second. That's around 250,000 miles per hour. In professional astronomy, that 110 kilometers per second is the key number, because we plug that into gravity calculations in metric units, not in miles per hour. For your intuition, 250,000 miles per hour is much faster than any spacecraft we have ever launched, hundreds of times faster than a rifle bullet. But we are talking about motion over billions of years, not over a human lifetime. At this point you might think, if it's that close and heading toward us that fast, doesn't that automatically mean a direct hit sooner or later? This is where everyday intuition breaks. Galaxies are not solid plates sliding toward each other. They are mostly empty space. The visible disk of the Milky Way is about 100,000 light-years across. Inside that disk, typical stars are a few light-years apart, tens of trillions of kilometers, or tens of trillions of miles. That huge spacing means that even in a so-called collision, single stars almost never crash into each other. What really happens when galaxies merge is that gravity reshapes orbits. Groups of stars are pulled into new paths, spiral arms stretch and twist, long streams of stars are pulled out into space, and some stars are ejected entirely from the system. The word collision makes you think of metal crumpling and explosions, but on the scale of a galaxy, it is more like a slow rearrangement of orbits. So why did we think this rearrangement was not only possible but inevitable? One major reason is that Andromeda is an odd case compared to most other large galaxies we can see. When astronomers measure the light from distant galaxies, they see most of them redshifted. That redshift means those galaxies are moving away from us, their light stretched by the expansion of the universe. Andromeda is different. Its light is blue shifted. Instead of its spectral lines being stretched to longer redder wavelengths, they are shifted slightly toward the blue. That is the signature of motion toward us. In a universe where most big galaxies are being carried away by expansion, our nearest large neighbour is one of the rare ones actually moving in our direction. But simply, the Milky Way and Andromeda are both massive. They are relatively close together on cosmic scales, and the net motion you see is them falling toward each other under their combined gravity. Given that a picture, it sounded reasonable to say sooner or later they have to meet. That is the mindset that fed the certain collision story. But there is a missing piece in that argument, a direction of motion you do not get just by looking at the colour shift of the light along our line of sight. You also need to know how fast Andromeda is moving sideways across the sky, not just toward us or away from us. That sideways motion is called the tangential velocity. For something that far away, the angle it moves each year is incredibly tiny. Astronomers measure that in micro-arcseconds per year, a millionth of an arcsecond, which is already a tiny fraction of a degree. It is far below what you can see with your eye or with a normal telescope over a human lifetime. And that is the crux of the whole story. For a long time, we had a good measurement of how fast Andromeda is coming toward us along the line of sight, but almost no direct handle on how fast it is drifting sideways. And here is the catch. Small changes in that sideways speed completely change the long-term outcome. If the sideways component is very small, compared to the head-on speed, the orbit is almost a straight fall in. If the sideways component is larger, even by a few tens of kilometers per second, the path can bend into a wide arc and miss a direct hit. So when you heard the collision is certain, it was really code for "we think the sideways motion is close to zero." That assumption became the backbone of those dramatic timelines, the 4 billion year countdowns, and the Milky story you might have seen in videos. The problem is that sideways motion is exactly the thing that is hardest to measure, and as soon as better data arrived, the word certain started to fall apart. And that sets up the next key piece in this saga. How do you actually measure the full motion of a galaxy across space? Not just toward you, but also across your field of view, when the angles are microscopic and the timescales are longer than human history. The first step is to nail down the easy direction, the one we were most confident about, and then tackle the nightmare direction that decides whether our galaxy really has a fixed death date or not. So how do you actually pin down the motion of an entire galaxy in 3 dimensions, when from Earth it's just a tiny smear of light on the sky? The first piece is the one astronomy is really good at, the straight toward you or straight away from you part. You start with the Doppler shift. Andromeda's light contains very clean fingerprints from hydrogen and sharp lines at very specific wavelengths that we know from lab measurements. When you spread Andromeda's light into a spectrum and look at those hydrogen lines, you see they're shifted a bit toward the blue. That blue shift means the light waves are slightly compressed, which means Andromeda is moving toward us along our line of sight. If you measure that shift carefully, you get a radial velocity of about minus 301 kilometers per second relative to the Sun. The minus sign just means toward us. In more familiar terms, that's roughly 670,000 miles per hour. But again, for the physics, kilometers per second is what really matters. That number is not a guess. It's measured very precisely from the spectrum. But that's only the speed relative to the Sun, and the Sun itself is not sitting still. Our Sun orbits the centre of the Milky Way at around 220 kilometers per second, so you have to correct for the Sun's own motion around the galaxy, subtract out our local movement, and work in the Milky Way's rest frame. Once you do that bookkeeping, Andromeda's approach speed relative to the Milky Way's centre drops to about minus 109 kilometers per second, so roughly 110 kilometers per second toward us, or about 250,000 miles per hour. That number, about 110 kilometers per second inward, is what people mean when they say Andromeda is heading straight at us. It's the clean, high-confidence part of the velocity vector, the head-on component. But if you only know how fast something is coming toward you, and not how much it's sliding sideways, do you really know whether you're going to collide, or whether it just swings past at the last second? That's where the nightmare direction comes in. The sideways motion across the sky, the tangential velocity. This is the component that decides whether the Milky Way and Andromeda actually smash together, or just skim past each other in a very close, very dramatic flyby. At Andromeda's distance of about 780 kiloparsecs, which is 2.5 million light-years, even a pretty respectable sideways speed turns into a ridiculously tiny angular drift. Take 100 kilometers per second of sideways motion, about 220,000 miles per hour. On the sky, that corresponds to a proper motion of only about 27 micro-arcseconds per year. A micro-arcsecond is a millionth of an arcsecond, and an arcsecond itself is just 1/36th of a degree. So you're now dealing with about 1 part in hundreds of millions of a degree per year. That is far below anything you can see by eye, far below what normal telescopes can track over a human lifetime. You're not watching dots crawl across a screen, you're comparing images taken years apart and trying to see if Andromeda's pattern of stars shifted by a fraction of a pixel against background galaxies even farther away that act like fixed reference points. So the tangential velocity is the crucial piece of information, but also the hardest to measure. You want it in kilometers per second, like the radial part, but what you directly observe is this tiny angular change in micro-arcseconds per year, and you have to convert that angle, multiplied by the 780 kiloparsec distance, into a linear speed. Any small error in the angle blows up when you multiply by millions of light years. If that sideways speed is the difference between hit and miss, and it's buried in noise at the edge of what your instruments can do, how confident can you really be about the fate of the Milky Way? This is why for a long time astronomers talked about limits and ranges instead of a single clean number. If the tangential component is very small, compared to the 110 km per second radial component, the orbit is almost radial, almost a straight fall inward. That's the most dramatic scenario, the one where Andromeda basically dives into us. Early work could only say that the sideways speed seemed to be less than about 200 km per second. That doesn't sound too bad until you think about what that actually means. Between 0 and 200 km per second, you have a huge cone of possible velocity directions. Some of those directions give you a direct hit, some give you a close miss, where the galaxies swing around each other and maybe merge later, maybe not. Some give you a much wider flyby where they strongly interact but never fully blend. When teams ran simulations with different tangential velocities inside that allowed range, the results were all over the place. You keep the same distance, about 780 kiloparsecs. You keep the same radial speed, about 110 kilometers per second. Then you dial the sideways speed up and down by just a few tens of kilometers per second. Suddenly, over billions of years of simulated time, the fate flips from tight, fast merger to very long, slow dance, to almost miss where they barely graze each other's halos. So tangential velocity near zero effectively meant we're doomed to merge, and tangential velocity modest but non-zero meant the story is way more complicated. And for years, nobody could tell which of those was actually true. If the sideways motion is this hard to get, why not just lean on what we do know really well, the radial speed and the current distance, and ask what those tell us about the system? That brings in another piece of physics, where motion doesn't just tell you about orbits, it tells you about mass. There's a classic argument astronomers use, sometimes called a timing argument. You look at the present separation between the Milky Way and Andromeda, about 780 kiloparsecs. You look at the present approach speed, about 110 kilometers per second. Then you assume that early on after the Big Bang, these galaxies, or rather their building blocks, started out moving almost with the general expansion, nearly at rest relative to each other apart from that. Over billions of years, their mutual gravity slowed their separation, then reversed it, and now they're falling together. If you know how far apart they are and how fast they're coming together now, and you assume they've been interacting gravitationally for the age of the universe, you can estimate the total mass needed for gravity to pull that off. Do that calculation in metric units, with distances in meters, speeds in meters per second, and the gravitational constant in its standard form, and you get a combined mass for the local group on the order of a few trillion times the mass of the Sun. That mass is not mostly in stars. If you add up all the visible stars and gas, you only get a small fraction of that. The bulk has to be in dark matter. This invisible mass that doesn't emit light but does feel and cause gravity. In other words, by watching how fast Andromeda is moving and how far away it is, you're not just plotting its future path, you're weighing the invisible halos of both galaxies at the same time. But there's a catch again. This argument assumes a fairly simple history, and it also assumes you really know the full velocity vector, not just the radial part. If you're wrong about the sideways speed, you're wrong about the exact orbit, and that feeds back into how you interpret the mass. So even your weigh the local group trick gets tangled up with this same missing piece of information. That's the observational cliff astronomers were standing on for decades. On one side you had a very precise radial velocity, measured from Doppler shifts down to a few kilometers per second. On the other side you had only a fuzzy, indirect idea of the tangential motion, with huge uncertainties. That combination made a future collision entirely plausible and very popular in models, but not logically forced. So how did plausible quietly turn into certain in the public story? It happened when one instrument finally claimed to detect that sideways motion directly, and the best fit answer came out very close to zero. That single result was enough to lock in the dramatic headline. How do you decide the fate of an entire galaxy based on a shift that's smaller than a pixel over a few years? That's exactly what happened in 2012, when Hubble stepped in and for a while closed the case on the Milky Way Andromeda story. A team of astronomers took Hubble images of Andromeda that were separated by about 5 to 7 years. Same regions, same telescope, years apart. They weren't just looking at the pretty spiral, they were using Andromeda's own stars as test particles. In each field, they picked out thousands of individual stars that belonged to Andromeda, and behind them, even farther away, they identified background galaxies that are so distant their own motion on the sky is basically zero for our purposes. The idea was simple in concept, brutal in execution. You measure the positions of Andromeda's stars relative to those background galaxies in the first set of images, then you measure them again in the later set, and you see if there is any tiny systematic shift. Not the internal swirling of stars in Andromeda's disk, not random motion, but the net drift of the entire galaxy on the sky. That net drift is the proper motion, the angular motion per year, and from that, combined with a distance of about 780 kiloparsecs, you can get the tangential velocity in kilometers per second. This was a first. Nobody had ever directly measured the proper motion of a massive external galaxy like this before. Remember how small that motion is? We're talking on the order of a few tens of micro-arcseconds per year, tiny slices of an already tiny angle. Hubble had to push its stability and calibration to the limit, correcting for distortions in the camera, tiny drifts in pointing, all of it, just to squeeze out that one sideways number. So what did they actually get, once they fought through all the systematics and subtracted every effect they could think of? After removing Andromeda's own internal rotation because its disk is spinning, and after correcting for the reflex motion from the Sun's orbit around the Milky Way, they ended up with a tangential speed of about 17 kilometers per second, with an uncertainty of plus or minus 17 kilometers per second. In miles per hour, that's roughly 38,000 plus or minus the same again, but the key is the size of the error bar compared to the value. Statistically, that result is completely consistent with zero sideways motion. In other words, Hubble's best estimate said Andromeda is falling almost perfectly straight in toward us, with only a tiny sideways drift, and that tiny drift could even be nothing at all. The big radial component, about 110 kilometers per second toward us, dominates. The sideways piece is so small within the uncertainties that the orbit looks nearly radial. In practical terms, that screamed head-on plunge. This is what people mean when they say nearly radial in this context. You have a big inward speed, a tiny sideways speed, and the error bars are large enough that the true sideways speed might be zero. If you were worried about the difference between a glancing blow and a direct hit, this pushed you very hard toward direct hit. Now, once you think you know the full velocity vector, the radial part and the tangential part, you can feed that into simulations and ask it a much more detailed question. Not just will they collide, but when and what happens next. That's where n-body simulations come in. You tell the computer, here is the Milky Way, give it a dark matter halo of around 1 to 1.5 trillion times the mass of the Sun. Here is Andromeda. give it a similar mass range. Put them 780 kiloparsecs apart, give them the measured relative velocity, and let gravity run the show. When teams ran those simulations with the Hubble-based velocity, they got a clear pattern. First close passage, where the galaxies really start to tear at each other's disks in about 4 billion years. After that, a couple of oscillations, where they swing through each other's halos and disks, lose orbital energy through dynamical friction, and then, over about 6 to 7 billion years from now, they settle into a single merged galaxy. That final system is not a nice clean spiral anymore. It's more like an elliptical or a big puffy lenticular galaxy, sometimes nicknamed Milkomeda. That timeline had another hook. 4 to 7 billion years is roughly the same window when the Sun will be finishing off the hydrogen in its core. In standard stellar evolution models, the Sun has about 5 billion years of stable hydrogen burning left. After that, it swells into a red giant. So you had this neat dramatic story. As the Sun approaches the end of its normal life, the Milky Way itself is colliding and merging, a double apocalypse on cosmic scales. It's easy to see why that got attention, but there's a big difference between what the scientific paper actually said and what the public story turned into. In the technical language, the authors said the data favoured a nearly head-on collision scenario. They talked about confidence intervals, about allowed ranges of tangential velocity, about assumptions in the mass models. It was strong evidence, but it still had caveats. Outside the journals, that nuance pretty much disappeared. In press releases and media coverage, the line hardened from likely head-on to destined to collide. NASA released detailed visualizations and animations showing the two spirals deforming, passing through each other, and settling into a single smooth blob. Documentaries picked up those visuals. Articles started using phrases like "the fate of the Milky Way is sealed." For you as a viewer, that became the mental picture. The crash is booked, and all that's left is the long wait. Once that idea settles in, it feels permanent. You don't naturally think, this depends on micro-arcsecond measurements and dark matter halo assumptions that might change. You just store it as a fact. Andromeda will hit us. So what was missing? What were the weak spots in that Hubble result that most people never heard about? First, the time baseline. Hubble only had about 5 to 7 years between the images it used for proper motion. For something as far away as Andromeda, that is a very short time. A longer baseline, like 15 or 20 years, would shrink the uncertainty on the proper motion significantly. But in 2012, that data simply didn't exist. Second, the coverage. Hubble didn't measure the motion of the entire galaxy uniformly. It observed 3 small fields in Andromeda's disk and halo, tiny patches compared to the full size of the galaxy. That means you have to model and remove the internal motions, the disk rotation, streaming motions, local substructure, and then assume what's left is the bulk motion of the galaxy's centre of mass. If any of those internal motions were not modelled perfectly, they could bias the result by a few tens of kilometres per second. Remember, that is exactly the scale at which direct hit and close flyby diverge over billions of years. On top of that, the formal uncertainty they quoted, about plus or minus 17 kilometers per second on the tangential speed, still allows a range of possible true values. At the high end of that range, the orbit is not as perfectly radial as the headline suggests. All of that means that even in 2012, a non-radial orbit was not ruled out. You could still have a scenario where Andromeda doesn't actually merge with us within the time window people care about, but instead swings past at a few 100,000 light years, warps the galaxies, and then takes a much longer time to settle, if it ever does. Those caveats were in the technical papers, but collision confirmed was a much more satisfying headline. So that's what stuck. For about a decade, that was the story you heard. Hubble has settled it. The galaxies will merge. The tension now is obvious. If Hubble seems so definitive, who or what could possibly overturn that story? The answer is, you need even more precise measurements over a longer time for many more stars and galaxies. And that's exactly what the next mission was built to do. Hubble looked like it had settled the question, so the obvious next question is this. Who gets to fact-check a space telescope that already pushed right up against the limits of measurement? The answer is Gaia, and Gaia was built exactly for the kind of tiny motions that decide whether our galaxy really crashes or not. Gaia is an ESA mission, whose whole job is precision astrometry, basically map-making in 3D. It measures the positions, distances and motions of stars with ridiculous precision, down to tens of micro-arcseconds. Over its mission, it's been tracking more than 1 billion stars in the Milky Way. It does this again and again, year after year, so it doesn't just know where a star is, it knows how that position changes with time. From those tiny shifts, you get parallax, which tells you distance, and proper motion, which tells you how the star is moving across the sky. Gaia wasn't designed primarily for other galaxies, it was built to map our own. But its instruments are so precise that the brightest individual stars in Andromeda's disk still show up. They are faint compared to Milky Way stars, but they're there. And if you can track their positions for a decade, you can try to squeeze out the same kind of proper motion signal Hubble went after, only with way more stars and a longer time baseline. So with a mission like that in play, do we see Hubble's story confirmed, or does everything start to wobble? When Gaia's early data release 3, EDR3, came out, several teams jumped on the Andromeda problem. Instead of a few tiny Hubble fields, they could now use thousands of bright Andromeda disk stars that Gaia had measured multiple times. The trick was similar. Model the internal rotation of Andromeda's disk, the random motions of stars and the Milky Way foreground contamination, then pull out the overall drift that tells you how Andromeda's centre of mass is moving across the sky. The first serious Gaia-based checks didn't scream everything changes. They found tangential velocities for Andromeda of order 40 to 60 kilometers per second in different components. That's about 90,000 to 135,000 miles per hour. The error bars were still large, so those numbers weren't razor sharp, but they were enough to say this: the orbit still looks mostly radial, the galaxy is still very clearly coming toward us, and broadly, Hubble's picture of a strong approach wasn't wrong. But there was a new twist hiding in those numbers. Tangential component in the 40 to 60 kilometers per second range is not the basically zero that the 2012 headline made you think of. It's still consistent within uncertainties with something closer to Hubble's value, but it already hints that there might be more sideways motion than that original 17 plus or minus 17 kilometers per second estimate suggested. And you already know the stakes. Add a few tens of kilometers per second sideways, and over billions of years, you can push the system away from a clean, fast merger. So if Gaia alone is already hinting at extra sideways motion, what happens when you combine its data with Hubble's earlier images and treat them as one long continuous record instead of separate snapshots? This is where the time baseline becomes critical. Hubble gave you about 5 to 7 years of motion. Gaia adds roughly a decade on top of that. Put them together properly, and now you're tracking Andromeda's position on the sky over 15 years or more, not just a short window. That longer baseline does two important things. First, it shrinks the statistical uncertainties. If you watch a tiny drift for 3 times as long, the total shift you're measuring is about 3 times bigger, which makes it easier to distinguish from noise. Second, it helps you deal with systematic effects. The subtle biases that come from things like the way Andromeda's rotating disk makes different regions move slightly differently, or how instrument distortions change over time. With more epochs and different instruments, you can cross-check, calibrate, and see which parts of the signal are real and which are artifacts. In plain terms, the longer lever arm lets you pull harder on the truth. If Hubble was close but slightly biased by where it looked and how long it watched, combining it with Gaia's long-term wide-field coverage helps correct for that. You're still working in micro-arcseconds per year, but the error bars around your final proper motion shrink, and the centre of that error bar can shift away from the almost zero that powered the old collision story. But Andromeda by itself is only part of the local group. To really understand how this whole system evolves, you need the motions of everything else that matters gravitationally. This is where Gaia quietly becomes not just a Milky Way map, but a local group dynamics machine. Gaia is also picking up stars in the Triangulum Galaxy, M33, another spiral galaxy in our neighbourhood with a mass of a few hundred billion suns. It's measuring proper motions of dwarf galaxies orbiting the Milky Way and Andromeda, tiny companions whose stars act as test particles moving through the combined gravitational field. For many of these dwarfs, Gaia gives you full 3D velocities, how fast they're moving toward or away from us, and how fast they're drifting sideways on the sky. Once you have those, you're not just saying Andromeda is coming toward us at about 110 kilometers per second, you're building a full 3D dynamical model of the local group. You can see how the Milky Way, Andromeda, M33, and dozens of dwarfs all orbit around the common centre of mass, how much mass has to sit in each halo to explain those motions, and how those halos are likely shaped and distributed. That matters directly for the collision question, because the future orbit of Andromeda doesn't depend only on its current velocity. It also depends on how heavy each galaxy is, how extended their dark matter halos are, and how other massive neighbours like M33 and the Large Magellanic Cloud tug on the system. Get those wrong, and even a perfect velocity measurement won't give you the right long-term prediction. So now you have a new situation. You know the positions of the key players more accurately. You have better proper motions from Gaia, extended by Hubble's older images. You have mass estimates for halos that are tied to real motions of dozens of satellite galaxies, not just rough guesses. The next logical step is obvious, and it's where the tension really ramps up. You take all of that updated information and you rerun the future. Same basic physics, same gravity, but much better initial conditions. You let the simulated local group evolve for 10 billion years and see how often systems like ours actually merge and how often they only come close. When astronomers did that, the certain collision storyline didn't just get a small tweak, it started to crack right down the middle. Here's the part most people miss when they picture this collision in their heads, the part that quietly controls everything. The bright spiral disks you see in photos are not the main event. They're a thin, glowing skin wrapped around something much bigger and invisible that's actually doing the wrestling. The Milky Way's visible disk is about 30 to 40 kiloparsecs across, roughly 100,000 to 130,000 light-years. Andromeda's is similar. That sounds huge, but those disks sit inside dark matter halos that stretch several hundred kiloparsecs, pushing toward 1 million light-years across. Each halo carries roughly 1 trillion times the mass of the Sun. The stars and gas are only a small fraction of that total. They're basically tracer paint on top of the real mass. So when you talk about the Milky Way and Andromeda colliding, the real interaction is between two enormous, overlapping halos of dark matter. Those halos feel each other's gravity long before the visible disks ever come close. As they overlap, they tug, they slow each other down, and they set the stage for whether the bright spirals at the centre eventually merge or just swing past each other. The disks are along for the ride, but the halos are steering. Here's where a key complication kicks in, and it's one that directly messes with the collision odds. Our own halo is probably not sitting neatly centred on the Milky Way's bright disk, and it's not just the Milky Way and Andromeda in the ring. There's a smaller but still serious fighter pulling on us right now. The Large Magellanic Cloud, the LMC, looks like a small companion galaxy in the southern sky. For a long time, people treated it like a minor satellite, just a pretty blob. Recent work says otherwise. Its mass is on the order of 100 billion suns, about 10 to the power of 11 solar masses, and the LMC seems to be on its first major infall toward the Milky Way, coming in fast and dragging a lot of its own dark matter with it. Because of that, the LMC's gravity can pull on the Milky Way's halo and disk hard enough to shift our galaxy's centre of mass by tens of kilometers per second. If the whole Milky Way stars and dark halo together is being yanked slightly in one direction, then the velocity of the Milky Way you use in the Andromeda calculation changes too. You're not standing on a fixed platform watching Andromeda come in, your own platform is sliding because of this satellite. Tens of kilometers per second doesn't sound like much compared to 110 kilometers per second of approach speed, about 250,000 miles per hour. but you already know the scale of the problem. Changes of a few tens of kilometers per second in the sideways or overall relative velocity are exactly what separate guaranteed merger from maybe just a close pass. So every time we revise how much the LMC is pulling us, we're also revising the Milky Way Andromeda trajectory. And the LMC isn't the only extra player quietly changing the script. There's another significant galaxy tied into Andromeda's halo, M33, the Triangulum Galaxy. Its mass is a few times 10 to the power of 11 solar masses, a few 100 billion suns. It orbits in Andromeda's larger dark matter halo, and its own orbit carries angular momentum, sideways motion and energy that can be exchanged with Andromeda and, indirectly, with the Milky Way. Depending on the exact path M33 is following around Andromeda, it can do one of two broad things to our future. If its orbit funnels angular momentum inward, it can help drive Andromeda more directly toward us, tightening the fall. If instead it pulls angular momentum out or tilts the system, it can shear the orbit, stretching it into something wider and longer period. Over billions of years these exchanges matter, and in simulations whether M33 has already had a close pass with Andromeda, or is only now falling in for the first time, changes how Andromeda moves relative to us. So now you've got at least four big masses in play: the Milky Way, Andromeda, the LMC and M33, all embedded in their own halos and nested inside a larger structure called the cosmic web. That bigger environment isn't just background decoration, it's part of the dynamics. When astronomers reconstruct galaxy motions over tens of megaparsecs, they find that the Milky Way and Andromeda don't sit in empty space, they lie inside a kind of flattened sheet of matter, with nearby galaxies sliding along that sheet, and big underdense voids on either side. This sheet versus void layout helps explain a key puzzle. Why is Andromeda moving toward us when most other large galaxies are receding? Because of cosmic expansion. There's a local flow along this sheet where the Milky Way and Andromeda are both falling toward the same dense region. Their mutual gravity plus the structure of the sheet drives them together, while more distant galaxies slide away along different directions. All of these pieces feed into one simple but brutal truth about the collision question. It's not just about one clean number for Andromeda's speed, it's about the full energy budget of the Milky Way Andromeda system inside this larger environment. The halos carry most of the mass. Satellites like the LMC and M33 can shove those halos around. The surrounding sheet and the void shape the larger scale flows. Change the assumed halo masses by only 20 to 30%, still well within the uncertainties. And you change how tightly bound the pair is. Make the halos a bit heavier, and gravity wins more strongly, pulling the galaxies together faster and making a merger more likely. Make them lighter, and the galaxies might only just be bound, or even end up marginally unbound, passing by each other slowly instead of falling all the way in. Even small shifts between where the visible disks sit and where the true centers of the halos lie can change the effective orbital energy. If the Milky Way's disk is offset inside its halo because of the LMC, and Andromeda's disk is offset because of M33 and other satellites, then the velocity you infer from the bright parts is not exactly the velocity of the real centers of mass. That difference is enough to change whether the two halos spiral together quickly, barely manage to capture each other, or stay in a loose, drawn-out dance. So the question you thought was simple, are we going to collide with Andromeda or not, turns into a delicate balance of dark matter mass, satellite kicks, and large-scale structure. Once you see that, there's an obvious next step. If the outcome is so sensitive to these details, what actually happens when you plug all the updated Gaia-era numbers into big simulations and let them run the future of the local group? You'd think that once you know everyone's speeds and masses, the future is basically locked in, right? You measure Andromeda, you measure the Milky Way, you punch the numbers into a simulation, and the answer is either yes, we collide, or no, we don't. That sounds clean. But when teams actually reran the problem with Gaia-era data and better mass models, The story stopped being a single clean line and turned into a whole cloud of possible futures. The first step was to stop pretending there is one best orbit. With Gaia-based proper motions, refined mass estimates for the Milky Way, Andromeda, M33, and the Large Magellanic Cloud, plus better constraints on the local group environment, astronomers built new n-body simulations that treat every massive object as a particle feeling gravity from every other one. Instead of picking one set of numbers and pressing go, they sampled thousands of different initial conditions, all of them consistent with the data within the error bars. So you don't get one future, you get an ensemble of futures. Each run takes the same basic measurements: current distances in kiloparsecs, velocities in kilometers per second, halo masses in units of the sun's mass, but jitters them within the allowed uncertainties. Then gravity evolves the system over billions of years. At the end, you count how many runs gave a fast merger, how many gave a slow merger, and how many gave only a flyby. That's how you turn "we have measurements with uncertainties" into "here are the odds of each outcome." Once those more realistic simulations were running, one of the first things that changed was the timing. Earlier models, based on simpler assumptions and Hubble's nearly radial orbit, put the first close passage in about 4.0 to 4.5 billion years. That's already far beyond any human timescale, but still within the remaining normal lifetime of the Sun. With updated inputs, the first pericenter, the first real close swing-by, slid back to around 4.3 billion years from now. That doesn't sound like a dramatic change, but it's a signal that the orbit is not quite as tight as we thought. And then comes the bigger shift. In many of these new simulations, if a full merger happens at all, it tends to land in the 8 to 10 billion year range, not 6 to 7. That means a complete blend of the Milky Way and Andromeda into one final galaxy is pushed into a time when the Sun is no longer a normal star. In standard stellar models, the Sun leaves the main sequence at around 5 billion years from now. By 8 to 10 billion years, it has already gone through its red giant phase and faded into a white dwarf. Long before those late merger stages, Earth's surface would have been uninhabitable for billions of years, simply from solar evolution, not galactic violence. So the neat galactic crash right as the Sun dies storyline starts to fall apart. The two clocks, stellar and galactic, no longer line up in a cinematic way, and that's before you even look at how sensitive the whole system is to tiny tweaks. Here's the uncomfortable part, the part that really breaks the idea of a scripted fate. In these updated simulations, if you vary Andromeda's tangential velocity by just a few tens of kilometers per second, you get completely different fates. Keep everything else the same, shift the sideways speed within the current error bars, and in one run you get a tight merger after a couple of passes. In another, you get long period oscillations, where the galaxies swing through each other's halos but take many tens of billions of years to fully settle, if they ever do. In another, the pair is only marginally bound, they come in, brush past, trade energy, and they never quite fall all the way together. This is chaos in slow motion. Not chaos in the sense of random noise, but in the sense that tiny changes now at the level of maybe 20 or 30 kilometers per second out of total relative speed of a bit over 100 lead to massively different outcomes billions of years later. The "and" in Andromeda stops feeling like a solid Milky Way and Andromeda will merge, and starts feeling more like Milky Way and Andromeda can do a whole menu of things depending on details we are still nailing down. But why does a system of only a few big galaxies behave this way? One of the main reasons is something called dynamical friction. Every time a massive galaxy moves through another galaxy's dark matter halo, its gravity pulls on that halo and creates a sort of wake, a region of slightly higher density trailing behind it. That overdense wake pulls back on the moving galaxy, acting like a drag force. It's not friction in the everyday sense of rubbing surfaces, but the effect is similar. The galaxy loses orbital energy and gradually spirals inward. How strong that drag is depends on how dense and concentrated the halos are. If the halos are very dense in the center, You get strong dynamical friction, the galaxies lose energy faster, and they merge more quickly. If the halos are more spread out, less concentrated, the drag is weaker, and the galaxies can keep a lot of their orbital energy, stretching the interaction out or even preventing a full merger within the time window you care about. Right now, we don't know the exact density profiles of the Milky Way and Andromeda halos. Observations and simulations suggest some general shapes, but there is room to adjust how cuspy or chord they are. In the new simulations, changing those halo profiles within the allowed range is enough to flip Andromeda from definitely sinks into us to sails on after a strong interaction. So even if you knew the velocities perfectly, the dark matter structure would still inject uncertainty into the final outcome. And then there's the twist that makes the whole thing even more unstable. Some of these simulations show that the Milky Way might not wait for Andromeda at all. Instead, we might first merge with the Large Magellanic Cloud in roughly 2 billion years, well before any strong encounter with Andromeda. Remember, the LMC is around 100 billion solar masses, and it's likely on its first infall. In many runs, dynamical friction between the LMC and the Milky Way's halo pulls the LMC inward fast enough that it merges with us on that timescale. If that happens, the Milky Way changes in a big way before Andromeda really arrives. Our galaxy's mass jumps, its shape gets more disturbed, its dark matter halo gets reshuffled, and its centre of mass shifts. The velocity of the post-merger Milky Way plus LMC system relative to Andromeda is not the same as the velocity we measure today. The whole starting point for the later Andromeda encounter gets rewritten. That pre-merger with the wrong partner means any simple story like Milky Way and Andromeda will do X is almost guaranteed to be incomplete. By the time Andromeda gets close enough for the main event, the Milky Way might already be a different galaxy dynamically. It might be more massive, more elongated, with a different motion through the local group. That again feeds back into whether Andromeda ends up on a plunging orbit, a grazing one, or something even more drawn out. So at this point, you're looking at a future where small changes in tangential velocity, small shifts in the halo structure, and even side mergers with satellites all combine. The outcome is no longer a clean yes or no. It's a probability distribution over many possible paths. That sets up the key question the next big study tried to answer directly. Given everything we know right now, what are the actual odds that the Milky Way and Andromeda really do merge within the next 10 billion years? So after all that work updating the models, what's the bottom line? Do we crash into Andromeda or not? In 2025, a team led by Tilsawala finally put a number on it, and it's not the number you were trained to expect. They took the latest Gaia and Hubble measurements, added in up-to-date mass estimates for the Milky Way, Andromeda, M33, and the Large Magellanic Cloud, and then ran huge suites of simulations tuned to look like our local group. The result is blunt. There is only about a 50-50 chance that the Milky Way and Andromeda will collide within the next 10 billion years. That's not destined, that's a coin flip. In fact, the way they phrase it in the Nature Astronomy paper is even sharper. There is a probability close to 50% that there will be no Milky Way-Andromeda merger at all in that 10 billion year window. So all those old diagrams that treated the merger as a scheduled event were only showing you one branch of a much messier decision tree. The numbers get even more striking when you limit yourself to the timescale you probably care about instinctively, the rest of the Sun's normal life. The same study estimates that the chance of a full Milky Way-Andromeda merger within the next 5 billion years is less than about 2%. That's the time it takes the Sun to finish burning hydrogen in its core and leave the main sequence. In plain language, the guaranteed crash before the Sun dies line is gone. There is now a very high chance that the Sun will go through its whole normal lifetime without ever seeing a completed Andromeda merger. So how did the odds fall from almost certain to basically a coin toss? There are three main reasons, and all of them tie back to things you've already seen building in the background. First, the tangential velocity is no longer treated as basically zero. When you combine Hubble's proper motion work with Gaia's long baseline and better statistics, the best fit sideways speed comes out a bit higher than the pure radial scenario implied in 2012. it's still not enormous. We're talking a few tens of kilometers per second sideways, compared to about 110 kilometers per second head-on. But that's exactly the scale where fall straight in turns into curve around and possibly miss. Second, the mass models got more realistic. The new work explicitly includes the Large Magellanic Cloud as a heavy hitter, around 100 billion solar masses, and M33 as another major satellite. The LMC's orbit runs roughly perpendicular to the Milky Way Andromeda line, and its pull actually makes a quick merger less likely by kicking the Milky Way's centre of mass sideways. M33, on the other hand, tends to increase the merger probability by pulling Andromeda a bit more toward us. When you put all four galaxies into the same model, Milky Way, Andromeda, M33, LMC, they don't cancel out neatly. They create a spread of possible orbits that's much broader than the old two-galaxy picture suggested. Third, the team didn't just simulate our exact system once. They also used cosmological simulations to look at lots of local group-like pairs, galaxies separated by around a megaparsec, with similar relative velocities and masses. Those analogues show that falling together now does not always mean merge quickly later. In many cases, pairs like this skim past, exchange some energy through their halos, maybe come back much later, or never quite spiral together within 10 billion years. When you fold that statistical reality into our specific measurements, the odds of an inevitable merger drop hard. Now here's the twist that really drives it home. The same year, ESA and NASA used more than a decade of Hubble data, combined with Gaia, to recheck the original destined crash story, and they ended up on the same page. Their press material straight up says there is only a 50-50 chance of the Milky Way and Andromeda colliding within the next 10 billion years. The telescope that gave you the 2012 head-on collision headline is now part of the evidence saying, actually, not guaranteed. They did this by extending the time baseline with later Hubble observations, tying them to Gaia's reference frame, and refitting the proper motion of Andromeda with better control of systematics. The net effect is that the allowed range of tangential velocities widens a bit and shifts away from the perfectly radial case. Still mostly an approach, still blue shifted at about 110 km per second, but no longer nailed down as a clean straight plunge. So your mental timeline just got snapped in half. For years, the story you heard was, we know the Milky Way will merge with Andromeda in roughly 4 to 5 billion years. Now the updated statement is, we don't actually know if they will merge at all in the next 10 billion years, and if they do, it's probably later than that. Scientifically, that's not a downgrade, it's an upgrade, because we've gone from pretending there is one fate to actually quantifying the uncertainty. Here's the part that feels weird from a human point of view. Nothing dramatic changed in the sky. Andromeda didn't suddenly veer off course. The Milky Way didn't get an emergency sideways kick last year. The only thing that changed was the data and the models. We measured the sideways motion better, we weighed the halos more carefully, we added the satellites properly, and then we admitted what the numbers really say. You went from certain collision to maybe not with no visible event, just a shift in how precisely we can track micro-arcsecond drifts over a couple of decades. That's the power and the humility of precision cosmology. When your whole prediction depends on tiny angles and small velocity components, even a 10 or 20 km per second update in the sideways direction is enough to flip the fate of an entire galaxy pair. So now the big question hanging over the story is this. If there's a solid chance that the Milky Way and Andromeda never fully merge, what does that future actually look like up close? What kind of near miss are we talking about? And how violent or calm is that scenario for the stars and any planets caught inside it? So what does a near miss between two galaxies actually look like, if they come close but don't quite lock into a full merger? In a lot of the new simulations, that's exactly what happens. Andromeda doesn't calmly stay put, it still dives in, but it just doesn't lose enough energy to get captured all the way. Instead of a head-on smash, you get a deep, fast pass. In those runs, Andromeda Galaxy still swings within a few hundred kiloparsecs of the Milky Way, something like 100 to 150 kiloparsecs, which is around 300,000 to 500,000 light years. Think of that in simple terms. That's only about 3 to 5 times the diameter of the Milky Way's visible disk. On cosmic scales, that's close. The halos overlap deeply. The disks feel strong tides, but the total orbital energy is just a bit too high for the system to lock together quickly. They exchange momentum, they curve each other's paths, and then they separate again, still bound or just barely bound, but not merged into one object. If getting that close doesn't count as safe, what does it actually do to the galaxies? Even without a direct overlap of the bright disks, the tides at those distances are not gentle. When two massive halos pass that close, their gravity stretches each other's disks and throws them slightly out of alignment. You can get warps in the outer regions, where the disk bends up or down instead of staying flat. Gas clouds in the disks get compressed, which can light up waves of new star formation, so-called starbursts, regions where stars are forming much faster than before. At the same time, some stars in the outskirts, especially ones that already sit in loosely bound orbits, get thrown out into long, thin structures called tidal tails. Those tails can stretch tens or even hundreds of kiloparsecs, which means up to hundreds of thousands of light years, or on the order of 1,000,000 trillion kilometers. That's a ridiculous number in miles too, about 1,000,000 trillion miles. From far away, those tails look like faint ribbons of stars and gas connecting the two galaxies, or streaming away behind them. But here's the key. In the near-miss cases, the dense central cores of the galaxies never fully sink into each other. Long after the closest approach, you still have two main galaxy centers, with their own bulges and central black holes, orbiting in the same general region of space but not blended into a single big elliptical. The outer parts may be shredded and mixed, but the hearts stay separate. So if they don't merge quickly, what do? Just drift apart forever? Not necessarily. In a lot of these non-collision scenarios, the Milky Way and Andromeda end up forming a very wide, long-period pair. They are still gravitationally linked, they haven't escaped each other completely, but the orbit becomes huge. You can picture a situation where, after the first close pass at a few hundred kiloparsecs, the galaxies fly apart to a separation of maybe a megaparsec or more, about 3 million light years, before slowly coming back in again. The orbital period can be tens of billions of years. That's far beyond the current age of the universe, about 13.8 billion years, and way beyond any timescale where the Sun or Earth's surface are still relevant. Meanwhile, dark energy keeps doing its thing, driving the accelerated expansion of the universe. Over those same tens of billions of years, galaxies outside the local group get pushed away so fast that their light eventually can't reach us anymore. So whether the Milky Way and Andromeda finally merge on some ultra-long orbit or just circle forever at a distance, they end up basically alone, with only a handful of local companions, in what's effectively an island universe. That sounds abstract, so what would it mean for anyone actually living inside a galaxy during a near-miss like this? From the point of view of a future planet orbiting a star in the Milky Way, you might still get a very dramatic ski. As Andromeda approaches pericenter, even if it doesn't hit us dead on, it will grow brighter and larger over the course of hundreds of millions of years. Right now, Andromeda is a small smudge a few degrees across in the sky. In a deep near pass, it could grow to span tens of degrees, a huge multi-armed structure dominating the night, much larger than the Moon's half-degree apparent size. You wouldn't see stars slamming into each other, you wouldn't see the Sun suddenly thrown into some wild, tight spiral. On human timescales, the changes would still be slow. Over thousands of years, the only obvious thing would be that the external galaxy in the sky keeps getting larger and more structured. Over millions of years, the background star field might distort as our galactic orbit is gently reshaped. Dynamically, the solar system would feel the near-miss mostly as a small change in its path around the galactic center. The local gravity of the Sun at 1 astronomical unit, about 150 million kilometers or 93 million miles, is still completely dominant over the tidal pull from Andromeda's halo at hundreds of thousands of light years away. So you're talking about a slow drift in where the whole system sits in the Milky Way, not a sudden ripping apart of planetary orbits. From the ground, it's a major light show, not a literal galactic car crash. So how is this still a big deal if the worst-case picture of a violent merger softens into a lot of warping, some starbursts, and a long dance? The change that really matters here is in how you think about the future, not in whether a particular tidal tail forms. For years, the story was presented almost like prophecy. We know this merger is coming, here's the date range, here's the final shape of the combined galaxy. Now, the same system with better data and more realistic models is described with probabilities. There's roughly a 50% chance they merge in 10 billion years and a 50% chance they don't. That shift from 99% certain crash down to coin toss is not just a small correction. It means the universe is under no obligation to give you a simple cinematic fate. When you actually follow the real dynamics, velocities with error bars, dark matter halos with uncertain profiles, satellite galaxies tugging from awkward angles, destiny turns into a spread of possible outcomes. Instead of one fixed timeline where the Milky Way is guaranteed to die in a blaze of merging spirals, you now have a tree of options, full merger, near miss, very long binary orbit, and each branch comes with a percentage, not a promise. And that sets up the next question. If the merger itself is no longer guaranteed, what about you and your local neighbourhood? What happens to the solar system in all these different scenarios? And is there any version of the future where things get truly dangerous for us on the scale of planets and orbits? So here's the uncomfortable question you probably have in the back of your mind right now in any of these futures. Merger or near miss? Does any of this actually threaten the solar system? Or does something else get to decide our fate first? The first thing you have to lock in is that the sun runs on its own clock. It doesn't care what Andromeda does. Right now, the sun is in the middle of its hydrogen-burning phase, the main sequence. Standard stellar evolution models say it has about 5 billion years of that stable phase left. After that, the core runs low on hydrogen. The structure of the star changes, and the sun swells into a red giant. When that happens, the inner solar system is in real trouble, and this has nothing to do with galaxies. Mercury and Venus are very likely gone, engulfed. Earth may or may not be swallowed. That depends on details of mass loss and how Earth's orbit expands. But either way, the surface is done. Long before that engulfment, the sun's increasing luminosity makes the surface uninhabitable. That whole timeline is set by nuclear physics in the sun's core, not by galactic dynamics or dark matter halos. Whether Andromeda hits us or misses, that red giant phase is still coming on roughly the same schedule. So what if a merger really does happen at some point while the sun is still around? What does that look like from your orbital neighbourhood? Simulations where the Milky Way and Andromeda actually merge show that the sun's orbit around the galactic centre doesn't stay neat and circular. It can get kicked around as the big gravitational potential changes shape. In some runs, the sun ends up flung outward into the far halo, maybe 50 to 100 kiloparsecs from the centre. That's about 160,000 to 330,000 light years. In others, it gets pulled somewhat inward. The exact outcome depends on where in the disk we are when the real chaos starts, and how the merger geometry lines up. But even in those wildest cases, the solar system itself almost always stays intact. Star-star collisions are so rare that they basically don't happen, even in a crowded merger. The average distance between stars is a few light years, tens of trillions of kilometers, tens of trillions of miles. The chance that another star physically cuts through the inner few astronomical units around the sun is tiny. What changes is the orbit of the sun around the galactic center, not your orbit around the sun. You can put numbers on that. At one astronomical unit, about 150 million kilometers, or 93 million miles, the sun's gravity dominates hard. The tidal forces from a passing galaxy's mass sitting tens of kiloparsecs away, tens of thousands of parsecs, hundreds of thousands of light years, are extremely small compared to the sun's pull at Earth's distance. To rip Earth away from the sun, you would need tides comparable to or stronger than the sun's own gravity. and Andromeda's halo at that range just doesn't get close. On the scale of your orbit, a merger is more like a slow, gentle tilt in the whole stage you're sitting on, not someone punching the floor out from under you. In a near-miss scenario, where Andromeda swings by at a few hundred kiloparsecs and never fully sinks in, the effect is even milder. The Milky Way's halo and Andromeda's halo still exchange momentum, so the Milky Way's centre of mass motion changes slightly. The shape of the combined gravitational field gets tweaked, and your galactic orbit adjusts. But the change is tiny when you zoom down to solar system scales. Over billions of years, the position of the Sun in the galaxy shifts a bit differently than it would have, but on human timescales, nothing about the sky suddenly screams galactic near miss just happened. The most dramatic thing a distant future observer might notice in a near-miss case is the slow evolution of Andromeda's apparent size and shape in the sky, and maybe subtle changes in the distribution of stars if you track them for tens of millions of years. Your day-to-day orbital mechanics around the Sun, though, stay boringly the same until the Sun itself starts turning up the heat. So in terms of genuine physical danger to orbits and planets, the hierarchy is simple. The Sun's own evolution dominates. Galactic mergers and flybys move you around inside the galaxy, but they do not tear your system apart. That doesn't mean the very far future is calm though, because on the larger scales, the universe is doing something slow and brutal in the background. Go far enough into the future, much farther than the 5 billion year main sequence lifetime of the Sun, and a different effect takes over the story. Cosmic expansion plus the fact that the local group is gravitationally bound. Our little cluster of galaxies, Milky Way, Andromeda, M33, a few dozen dwarfs, is held together by its own gravity, so it doesn't get torn apart by dark energy. But everything outside this region does drift away faster and faster. As time goes on, distant galaxies cross a kind of visibility horizon. Their light gets so stretched and delayed by expansion that it can no longer reach us. Whether the Milky Way and Andromeda merge into one big elliptical or stay as a wide pair, the net result is the same. The local group becomes a lonely island in an otherwise empty-looking universe. The night sky, for any observers still around, is no longer a web of thousands of galaxies scattered across deep images. It shrinks down to just a few local systems, or maybe a single big galaxy surrounded by faint remnants. That's the real end of the universe from the point of view of observers, not a single dramatic collision, but a slow fade out of everything beyond your own gravitational bubble. The details of the Milky Way-Andromeda interaction change the internal view, one big elliptical versus two warped spirals, but either way, the large-scale backdrop collapses to almost nothing. So if your own orbit is stable, and the real danger comes from the Sun and the eventual isolation of the local group, is there any part of this story where we still get a truly extreme event? Something like a titanic collision that could send shockwaves across the universe, even if we never feel it directly. The part of this story that sounds the most like a sci-fi trailer is the one that now might never happen, the duel between the giant black holes in the centres of the two galaxies. For years, people talked about that as if it was guaranteed, like the final boss fight waiting at the end of the Milky Way-Andromeda merger. How even that final showdown has to be downgraded from promise to maybe. Right now, both galaxies have central monsters. At the heart of the Milky Way sits Sagittarius A, a supermassive black hole with a mass around 4 million suns. In the centre of the Andromeda Galaxy there's another supermassive black hole, probably close to 100 million solar masses. That's roughly 25 times bigger in mass. And remember, mass is what drives gravity here. If the galaxies actually merge, the expectation from simulations is pretty clear. First, the dark matter halos and stellar bulges merge and settle into one larger potential. Inside that, the two central black holes start to sink toward each other. They lose orbital energy through dynamical friction, just like galaxies do in halos, but now inside a dense field of stars and gas. They form a tight binary at the core of the new galaxy, orbiting each other at high speed, and over time that binary shrinks. As the binary tightens, It enters a regime where it's no longer just exchanging energy with nearby stars and gas. It starts to radiate a lot of its orbital energy away as gravitational waves, ripples in space-time itself. The closer and faster it gets, the more power it pours into those waves, until finally the two holes coalesce into a single, even more massive black hole. On human scales, this is unbelievably violent. You're talking about tens of millions of solar masses moving at a significant fraction of the speed of light in the final orbits. The gravitational waves from a merger like that would be low frequency, with periods of years to hours, not the milliseconds you see in smaller black hole mergers we detect with ground-based detectors today. Those low-frequency waves are exactly the kind of thing pulsar timing arrays and future space-based observatories are built to catch. A Milky Way Andromeda black hole merger would ring space-time strongly enough that, in principle, a civilization with sensitive enough instruments in a nearby galaxy could detect the signal. We already run supercomputer simulations of events like this today, because they're a key part of how big galaxies grow in the standard cosmology picture, even if our own local pair never actually pulls it off. Right around those black holes, in the inner few parsecs, a few light years, orbits get brutal. When the galaxies interact and their cores finally mix, the orbits of stars near the binary are constantly being kicked and reshaped. Some stars get scattered inward and swallowed. Others get flung outward at escape speeds of thousands of kilometers per second, several million miles per hour. Those are the hypervelocity stars. Objects moving so fast they can leave the entire galaxy behind and wander off into intergalactic space. All of that drama is highly concentrated. It's a central few parsecs thing. By the time you're out at the sun's current distance from the galactic center, about 8 kiloparsecs, roughly 26,000 light-years, the effect of the black hole merger is much milder. The combined black hole is still just a point in the overall mass distribution. Its gravitational influence fades with distance, and the bulk of the gravity you feel out here comes from the galaxy's stars and dark matter, not the tiny central point. Our orbit might shift a bit in angle and radius as the global potential changes, but we are not in the splash zone of that core-level chaos. All of that depends on one big if, though. If there's no full galactic merger, there's no black hole showdown. In the flyby and long-period scenarios, the central black holes in the Milky Way and Andromeda never get close enough to bind into a tight binary. They stay inside their own bulges, sitting at the centers of their own galaxies, doing what supermassive black holes usually do in the quiet universe. That quiet life is not completely boring. They still slowly accrete gas and dust. They can flare when a gas cloud falls in, or when a star gets too close and is torn apart. But there's no guaranteed epic coalescence, no single stupendously bright gravitational wave event tying a bow on the Milky Way story. The universe has no obligation to give you a Hollywood climax just because you'd like one. The really important lesson in all this isn't just that the showdown might never happen, it's how easily that prediction flips. For a while, people spoke as if we knew, with confidence, that Sagittarius A would eventually merge with Andromeda's central black hole. Now the honest answer is, we don't know if they ever will. And that change came from tightening a sideways velocity by a few tens of kilometers per second and updating some halo masses. Think about that scale for a second. 10 or 20 kilometers per second is around 20,000 to 45,000 miles per hour. That's fast by human standards, but as a fraction of the 110 kilometers per second head-on speed, it's not huge. Yet when you run that difference forward over billions of years, in a system this big, it can decide whether two supermassive black holes ever even meet. That's the core message about long-term predictions in cosmology. When you're projecting billions of years into the future, small uncertainties today, in the 10 to 20 kilometers per second range or in the 20 to 30% range for halo mass, are not details, they are the whole story. They decide whether you end up with one final central monster or two separate, quieter ones that never touch. So if the future is that sensitive, how can you ever trust any prediction at all? The answer is, you don't just look forward, you also look backward. You use the scars and fossil trails already written into both galaxies to pin down their mass and history, and that in turn tightens what they can do in the future. The next piece of the story is about how we read those fossils, streams, dwarfs, and ancient collisions, to figure out what kind of Andromeda ending is actually allowed. If the future is so uncertain, how do you even start to pin it down? You don't just stare at Andromeda and guess. You look at the scars both galaxies already carry, and use those as hard clues about how much mass is there and how it's arranged. Around the Milky Way and around Andromeda, astronomers see long thin rivers of stars called tidal streams. These are not random, they are the remains of smaller galaxies that got too close and were pulled apart by gravity. When a dwarf galaxy falls in, the side closer to the main galaxy feels a stronger pull than the far side. It gets stretched, then shredded, and the stars are left on extended orbits that line up into streams. With modern surveys, you can measure the velocities of stars in those streams in kilometers per second, and their distances in kiloparsecs. For example, a stream might be 30 or 50 kiloparsecs out, roughly 100,000 to 160,000 light years, and its stars might be moving at a few hundred kilometers per second along very specific paths. When you plug those orbits into models of the Milky Way's gravity, you can ask, what total mass distribution makes this stream's path make sense? If the halo is too light, the stream doesn't curve enough. If it's too heavy or too concentrated, the stream wraps differently. You can do the same thing in Andromeda, where deep imaging reveals huge, complex streams in its outer halo. Together, these streams are fossil trails. They tell you where past mergers and flybys happened, and they lock in how strong the gravitational field has to be at each radius. That directly constrains the shape and mass of each galaxy's dark matter halo, and that feeds back into the question, will these halos eventually pull each other in or let each other go? Streams aren't the only fossils you can use. Both the Milky Way and Andromeda are swarmed by dwarf galaxies, much smaller systems orbiting as satellites. The Milky Way has a few dozen known dwarfs, like the Sagittarius dwarf and the Fornax dwarf. Andromeda has its own cloud of companions. Before Gaia, you could measure their line-of-sight velocities, how fast they're coming toward us or moving away, in kilometers per second. With Gaia's proper motions, many of these dwarfs now have full 3D velocities. Each dwarf is basically a test particle, orbiting in the combined gravitational field of its host galaxy, and on larger scales the local group. If the Milky Way were extremely massive, you'd expect certain ranges of orbital speeds and shapes for its satellites. If it were much lighter, you'd get a different pattern. The same goes for Andromeda. When you look at all the dwarf orbits together, the allowed mass range for the main halos gets squeezed down. On top of that, some dwarfs are moving fast enough that they're probably not tightly bound to just one galaxy. They're feeling the pull of the whole local group. Their trajectories tell you whether the Milky Way and Andromeda together form a deep gravitational well, or are only loosely holding each other. That's a direct check on whether a long-term merger is likely, or if a wide flyby is more natural. Even with all of that, you still have only one local group to look at directly. To understand how typical our situation is, and what systems like ours tend to do, you need a bigger sample. That's where cosmological simulations come in. In the standard lambda CDM cosmology, you simulate a big chunk of the universe, hundreds of millions of light years across, with dark matter, gas, stars, and expanding space. In that virtual universe, you find pairs of galaxies that look like the Milky Way and Andromeda, separated by about 1 megaparsec, around 3.3 million light years, with similar masses and relative velocities to ours. Then you watch what happens to those pairs over billions of years inside the simulation. Some of those analogues merge quickly. Some interact and emerge only after very long, slow orbits, and may swing past each other and never quite spiral in. By comparing the statistical fates of these simulated pairs with our actual measured properties, you can say, given everything we know, systems like ours merge about X% of the time within 10 billion years. That's where the 50-50 odds come from. It's not just one fancy orbit calculation. It's our local group set against thousands of digital cousins. All of this backs into one key number, the total mass of the local group. Current estimates put that total around 3 to 4 times 10 to the power of 12 solar masses. Roughly half of that is in the Milky Way and its halo, roughly half is in Andromeda and its halo, with smaller pieces in M33, the Large Magellanic Cloud, and dozens of dwarves. If that total mass were much larger, the two main halos would be more tightly bound, and a merger would be hard to avoid. If it were much smaller, the pair might barely be holding together, and a clean flyby or ultra-long period orbit would be more natural. The spatial distribution of that mass matters just as much. If most of the mass is packed close to the galaxies, you get strong dynamical friction when they pass through each other's halos, which helps them lose energy and merge. If the mass is spread out more diffusely or skewed by heavy satellites like the LMC, you can weaken that drag and change the whole future path. Now here's the part that really ties the whole thing together. The same data you use to reconstruct ancient collisions, like a dwarf galaxy that was torn apart 8 or 10 billion years ago, leaving a stream wrapped around the Milky Way, are the data that force you to update your predictions about the far future. Every time you improve a stream's orbit or a dwarf's proper motion, you tighten the mass model. Every time you tighten the mass model, you narrow the range of allowed Andromeda futures. You are literally using fossils, traces of galaxies that died long ago, to forecast whether your own galaxy ends up as a fossil inside a big elliptical, or survives as the still distinct spiral orbiting in a wide pair. Past mergers don't just tell you where we came from, they reach forward and reshape what we can honestly say about where we're going. And that brings up a very human question that sits underneath all this math. How did we get so comfortable turning one version of the story, we will definitely merge, into the new, uncomfortable answer, we might or we might not? What changed in how scientists talk about this? And what does that shift tell you about how science itself works when it's dealing with billion-year predictions? You've basically watched the Andromeda story go from we have no idea to we're doomed to actually we're not sure at all. And that whiplash didn't come from drama in the sky, it came from how humans handle data. That's the real human story under all the kiloparsecs and kilometers per second. Back in the late 20th century, the picture was pretty loose. Astronomers knew Andromeda was blue shifted. They knew it was moving toward us at around 110 kilometers per second, about 250,000 miles per hour, and they knew the Milky Way and Andromeda were the two main heavyweights in the local group. The sideways motion was basically unknown, so the line you would have heard then was something like, they're probably going to collide in a few billion years. Not guaranteed, not carefully quantified, just probably, because gravity plus a closing velocity usually means an eventual encounter. That vague probably left a lot of room for interpretation. Some popular science books leaned into the drama, talking about the distant future collision as if it were almost a fixed date. Others stayed more cautious, but there wasn't a single sharp headline yet, because the data weren't sharp. It was an open problem, and everyone kind of knew it. Then Hubble's 2012 proper motion result landed, and it felt like someone finally slammed the door shut. For the first time, there was a direct measurement of Andromeda's sideways motion that seemed to say, it's tiny. When you combine a strong inward speed of approximately 110 kilometers per second with a tangential speed that's maybe only a few tens of kilometers per second at most, your orbit looks almost head-on. The technical language in the paper talked about favouring a head-on collision scenario, but in practice the vibe shifted to almost certainly head-on. That's the version that went everywhere. Textbooks updated their diagrams, popular books added chapters about the future Milky Galaxy. Science communicators put out videos and infographics showing the two spirals merging over the next 6 to 7 billion years. You might have seen timelines with labels like First Pass 4 billion years and Final Merger 7 billion years, as if those were booked appointments. Why did that happen so quickly? Because there's a very human temptation here. Every time a new instrument arrives, you want to treat it as the final word. Hubble had incredibly sharp images. It had a long track record of breakthroughs, so when it pushed down into the micro-arcsecond per year regime and pulled out that first proper motion, it felt definitive. If Hubble says the tangential velocity is near zero, then you treat near zero as zero and move on. But that's where the difference between instrument bias and honest uncertainty kicks in. Hubble's measurement wasn't bad, it was just right at the edge of what that method and baseline could really handle. Gaia, longer time baselines, and better modelling of things like Andromeda's internal disk rotation and halo substructure all showed that the systematics are not trivial. If the disk is rotating, and you only observe a few specific fields, you can easily bias the result by tens of kilometers per second if your model isn't perfect. And tens of kilometers per second is exactly the danger zone. It's the range where smash and miss trade places. A 10 to 20 kilometers per second difference in tangential velocity doesn't sound like much, but over billions of years in a trillion solar mass potential, that's enough to send Andromeda on a deeper plunge or a wider loop. What looks definitive in 2012 started to look like one strong data point with sizable systematics when you put it next to Gaia and better halo models. By 2025, that rethinking had gone far enough that agencies stopped dancing around it. ESA, NASA, and independent teams were willing to say it plainly. The Milky Way Andromeda collision is not a guaranteed event. The updated numbers say roughly a 50-50 chance of a merger within 10 billion years, and a very low probability, under a few percent, that it completes within the next 5 billion years, while the Sun is still in its main hydrogen-burning phase. You can see this shift in how official materials are written. Old language, Milky Way and Andromeda are destined to collide. New language, there is a roughly 50% chance that the galaxies will collide in the next 10 billion years. Same agencies, same telescopes, different level of honesty about uncertainties. News outlets followed that lead. Headlines switched from "fate is sealed" to "collision less certain than previously thought," and "new study suggests 50-50 odds." The funny thing is, most of the raw facts you liked about the original story have not changed at all. Andromeda is still about 2.5 million light-years away. In metric, that's roughly 780 kiloparsecs. It is still coming toward us along the line of sight at about 110 kilometers per second, which is still about 250,000 miles per hour. Both galaxies are still giant spirals, each with a dark matter halo of around 1 trillion solar masses or more. The local group is still a few trillion solar masses in total. Gravity hasn't changed. The equations we use to evolve these systems, expressed in kilometers, seconds, kilograms, and so on, are the same. The expansion of the universe is still there. Dark energy is still making distant galaxies recede faster over time. None of that flipped. What changed is the trajectory we infer from the data. The sideways component of Andromeda's velocity isn't unknown anymore, and it isn't basically zero anymore either. It's something in between, measured but with non-negligible error bars. The mass of the Milky Way, Andromeda, M33, and the LMC isn't a rough guess anymore. It's a constrained set of values tied to streams, dwarfs, and proper motions. When you plug that updated state into the same physics, the future split into multiple branches instead of one fixed path. That's the deeper lesson here. Science, especially cosmology, is not a prophecy machine. It doesn't hand you the fate of the galaxy from some perfect oracle. It takes the best data you have right now, wraps them in a model, and gives you predictions with error bars. When the data get better, the error bars move. Sometimes they shrink around the same answer. Sometimes they move enough to flip the headline from certain to maybe. In the Andromeda case, those error bars were big enough and important enough that they turned a confident yes into "we don't know," and the true probability is around 50%. That's not a failure, that's the system working. You don't cling to the most cinematic answer, you update the most honest one. So now you're left with a story that feels less satisfying but more real. The future of the Milky Way Andromeda system is a probability distribution, not a single script. and the reason it's so sensitive is exactly the thing you've seen all along: tiny angles, small velocity components, moderate halo uncertainties. To really see why those small numbers matter so much, you have to look at the level of precision the field is chasing. The units, the tiny angles, and the way error bars actually decide the story. Here's the strange part you don't feel in your gut at all. The fate of two galaxies is hanging on numbers that look tiny and boring when you write them down. If you just go by intuition, you will get this story wrong every time, which is exactly why cosmology leans so hard on precise units and error bars. When astrophysicists talk about Andromeda, they don't think in miles per hour, they think in kilometers per second, parsecs, and solar masses. That's not snobbery, it's because the basic gravity formulas want those units. When you plug things into the law of gravity, mass times the gravitational constant divided by distance squared, everything is set up in kilograms, meters, and seconds, not in pounds and miles per hour. So a speed of 110 kilometers per second is clean in that system. It drops straight into the equations that evolve orbits over billions of years. If you rewrite that as roughly 250,000 miles per hour, it may sound more dramatic, but that version is basically useless if you're doing real calculations. You'd have to convert it back to metric before you can feed it into a simulation. Same with distances. Astronomers use parsecs and kiloparsecs because those units are tied directly to angles on the sky, and that makes the math simpler. A kiloparsec is about 3,260 light years. Andromeda is about 780 kiloparsecs away. That's how it shows up in the code. In miles, that's an absurd number of zeros that doesn't help you see how one part of the system compares to another. But if you only ever hear the metric numbers, it's hard to feel just how extreme they are. So you do still need some translations for your brain. So how do you turn 110 kilometers per second into something your everyday intuition can at least latch onto? Start with speed. 110 kilometers per second means in 1 second you've gone 110 kilometers, about 68 miles. In 1 hour, that's 110 times 3,600, so 396,000 kilometers, around 246,000 miles. That's the 250,000 miles per hour line you usually hear. At that speed, you could circle Earth at the equator in well under 10 minutes. Earth's circumference is about 40,000 kilometers, so divide 40,000 by 110 and you get a bit over 6 minutes. Compared to something familiar, that's roughly 900 times faster than a modern fighter jet, which cruises at maybe 0.3 kilometers per second, not 110. Distance is even worse for intuition. 780 kiloparsecs is about 2.5 million light years. 1 light year is about 9.5 trillion kilometers, so 2.5 million of those is roughly 1.5 times 10 to the power 19 kilometers. In plain language, that's 15 billion billiontian kilometers. The average distance from Earth to the Sun, 1 astronomical unit, is about 150 million kilometers. So Andromeda's distance is on the order of 100 billion times that Earth-Sun distance. Whether you say 1.5 times 10 to the 19 kilometers, or about 9 trillion miles times a few million, you're in a regime where normal yardsticks just break, so metric is what makes the formulas behave, and imperial is a tool you use to say, okay, that's like lapping Earth in a few minutes, or that's like stacking 100 billion Earth-Sun distances end to end. The numbers are extreme either way. The unit swap just decides whether they feel human or not. The really nasty part, the part your intuition is worst at, is not the speeds and distances, it's the angles. A big chunk of this whole story rests on proper motions, tiny apparent shifts of Andromeda on the sky, measured in micro-arcseconds per year. That's where your brain really checks out if you don't slow down for a second. Take a proper motion of 25 micro-arcseconds per year, a typical scale for Andromeda's sideways drift. 1 degree is the angle your pinky fingernail covers at arm's length, roughly. A degree can be split into 3,600 arcseconds. Now 1 micro-arcsecond is a millionth of an arcsecond, so you're talking about 25 millionths of 1/3 of 3,600 of a degree per year. If you turn that into a fraction of a degree, 25 micro-arcseconds per year is about 1 divided by the 140 million degrees per year. So if you drew a 1 degree wedge on paper and then tried to cut that wedge into 140 million equal slices, one of those slices would be the angle Andromeda moves across the sky in a year. Every proper motion measurement you've heard about, Hubble's, Gaia's, is hunting for changes at that level. That's the precision the collision versus flyby decision is hanging on. Not whole degrees, not even arc minutes, but tens of micro-arcseconds per year. When you hear that, the idea that small systematics or slightly different disk modelling can move your answer by 10 or 20 kilometers per second starts to sound a lot less surprising. This is exactly why error bars aren't decoration, they are the plot. When you read tangential speed 17 plus or minus 17 kilometers per second, your instinct might be to focus on the 17 and treat the plus or minus 17 as a tiny caveat. In this problem, the plus or minus 17 is the main character. If the true value is near the low end, close to zero, you get an almost radial plunge and a relatively fast merger. If the true value is more like 30 or 40 kilometers per second, still inside that error bar, you can end up with a much wider, slower orbit, possibly just a flyby. The same thing applies to mass. If your estimate for a dark matter halo is uncertain by a factor of 2, say it could be 0.8 trillion solar masses or 1.6 trillion, that's not a minor detail. In two-body gravity, going from barely bound to comfortably bound is very close to a factor of 2 kind of change in mass or energy. If the combined mass of the local groups sits near the lower end of the range, the Milky Way and Andromeda might only be weakly bound and move more like ships passing slowly in the night. If it sits near the high end, they're locked into a deeper potential and a merger is more likely. So every time you see a number like 110 kilometers per second in this context, you should be asking plus or minus what? And every time you see a distance or mass, you should be mentally attaching the allowed range. Because the fate of the system isn't tied to the central value alone, it's tied to the whole allowed region those error bars cover. Here's the twist that might feel backwards at first. The more precisely we measure these things, the less comfortable we are with simple destiny stories. As Gaia and Hubble shrank the error bars on Andromeda's proper motion, and as streams and dwarfs shrank the error bars on halo masses, the space of allowed futures got narrower, but it didn't collapse to a single line. Instead, it turned into a split, roughly a 50-50 split between merge within about 10 billion years and don't. That is not a failure of precision. That is what progress looks like in a problem like this. We've moved from hand-wavy talk of probably a collision to a quantified statement. Based on all current data, there's about a half chance they merge in 10 billion years and a very small chance they merge within 5. You've traded a fake sense of certainty for a real hard-won probability distribution. So now you're standing in front of a story that started as a scripted apocalypse and ended up as a set of odds. If even the fate of 2 massive galaxies can flip from certain to coin toss when you push the precision hard enough, what does that say about all the other "we know the fate of X" stories you've heard? And how do you wrap up a video about Andromeda without falling back into the same trap of pretending the universe has a neat ending? Right now, the odds sit around 50 to 50, but that number is not locked in at all. The Milky Way Andromeda story is still being updated in real time, and the missions that are already flying are basically loading the next round of corrections. So the real question isn't what are the odds today, it's what could still move those odds tomorrow. Start with Gaia. The spacecraft has finished its main observing phase, but the data releases are not done. Through the late 2000s, you're getting better and better catalogues, each one with longer time baselines and more refined calibrations. That matters directly for Andromeda, because every extra year of data lets Gaia see a slightly larger total drift on the sky, shrinking the random noise in the proper motion. Each release also improves the motions of local group dwarf galaxies. Those dwarfs are your test particles. They are what you use to nail down the Milky Way's and Andromeda's dark matter halos, and the overall local group mass. So every time Gaia pushes the uncertainty on a dwarf's proper motion down by a few micro-arcseconds per year, you're tightening the mass model that feeds the big simulations. future missions could go even further. A dedicated next-generation astrometry satellite with better stability or different wavelength coverage could push proper motion precision below Gaia's tens of micro-arcseconds per year, at least for a subset of bright stars. That would mean Andromeda's sideways speed and the velocities of key satellites get pinned down to within maybe 5 to 10 kilometers per second instead of 20 to 30 kilometers per second. And you already know what scale of change flips certain into coin flip in this problem. So if the sideways motion and the dwarf orbits get sharper, what else do you need to improve before you can say anything stronger about the collision odds? The next big lever is the structure of the halos themselves, and that's where the Vera C. Rubin Observatory comes in. Rubin is about to run a 10-year legacy survey of space and time, scanning the southern sky over and over. It's going to catch transient events, but it's also going to map faint structures in the outskirts of galaxies, including tidal streams around the Milky Way and around galaxies that look like Andromeda. Those streams are what you use to say, at 50 kiloparsecs, 100 kiloparsecs, this is how strong the gravitational field is. In units, that's tens to hundreds of thousands of light years from the centre. Rubin's deep, repeated imaging will make it easier to pick out streams that are currently right at the edge of detectability. Once you've traced those streams and measured the star's velocities in kilometers per second, you can clamp down on the halo shapes and densities much more tightly. And there's another angle. Rubin will see Andromeda analogues, other big spiral galaxies in small groups, in different stages of interaction. That gives you more real-world examples to cross-check against cosmological simulations, which shapes and stream patterns tend to come from fast impending mergers, and which from past flybys or stalled encounters. But what if we're wrong about the dark matter itself, not just about how much of it there is and where it sits? Most of these models assume dark matter is cold and collisionless, meaning the particles move slowly compared to the speed of light, and they barely interact with each other except via gravity. If that picture is slightly wrong, if dark matter has a weak self-interactions, or a non-trivial temperature, or multiple components, then halo structure changes. You can get cores instead of steep cusps, different density profiles, different responses to infalling satellites. That directly affects dynamical friction, the gravitational drag that slows galaxies down as they move through each other's halos. If dark matter clumps more efficiently in the centre, drag is stronger and mergers happen faster. If it's puffier or interactions smear out density peaks, drag is weaker and galaxies hang onto their orbital energy longer, making fast mergers less likely. Right now, we don't have a smoking gun reason to throw out cold, collisionless dark matter, but people are absolutely testing small deviations, and any solid detection of new dark matter physics would need to be fed back into Andromeda-style simulations. Even if the basic dark matter model holds, there's still a lot of room for surprises from the satellites we already know about, especially the Large Magellanic Cloud. The LMC's exact mass is still being refined. Is it 100 billion solar masses? 200 billion more? Its orbit is also still being pinned down in detail. The same goes to a lesser degree for the Small Magellanic Cloud and a couple of other heavy satellites. If the LMC is heavier or on a slightly different orbit than we think, the Milky Way's centre of mass moves differently. That changes the true velocity of the Milky Way relative to Andromeda by tens of kilometers per second. Once again, you're right in the danger zone where a few tens of kilometers per second decide whether the future is a tight merger or a long, loose dance. Better mapping of the LMC's stars, gas and dark matter, plus longer baseline proper motions from Gaia and Rubin, will keep shifting that relative velocity vector until the model finally settles. So where does that leave the actual collision odds? Are we stuck with 50-50 forever, or is that number going to wander around as the data tighten? The honest answer is that the odds can and probably will move. A decade from now, after Gaia's final data release, Rubin's early maps of streams and improved LMC modelling, the best fit probability might shift upward, maybe 60 to 70% chance of a merger in 10 billion years. or it might drop maybe 20 to 30% if the tangential velocity and mass budget are both just a bit higher than today's central estimates. The key point is not which way the number moves, it's that you're watching a live process. The universe is going from hand-wavy stories about destined collisions to hard dataset-driven probability statements. The Andromeda non-collision is possible headline is not the last word, it's just the current snapshot. The real final word, if there ever is one, will come from the next round of micro-arcseconds and stream maps. So when you step back, you're left with a different kind of cosmic cliffhanger. Not we know exactly how this ends, but we know this is a close, high-stakes situation, and the more precisely we look, the more we see how much is still open. The only thing left is to pull that tension together and ask what this whole Andromeda saga actually means for how you think about the future of the universe, and about any story that pretends to have a fixed ending. So here's the strangest part of this whole story. The more precisely we measured the future, the less it looked like a fixed ending. The clean version you grew up with was simple. 2 spiral galaxies, 1 unavoidable crash, roll credits on a giant elliptical. It felt neat, it felt final, and it slotted nicely into a fate of the Milky Way slide. The updated version is messier and more honest. Now you have 2 spirals embedded in a web of dark matter, dragging satellites, moving inside a local sheet of galaxies. The future is no longer one line, it's a set of branches. In some branches, they really do merge, just later and slower than you were told. In others, they loop past each other in a deep near miss, exchanging momentum but never fully blending. In others, they end up as a wide, weakly bound pair that takes longer than the next 10 billion years to settle, if it ever does. That's the new script, and it's not as cinematic, but it matches the data. So what can you actually say with a straight face right now without overselling or underselling anything? You can say Andromeda is moving toward us along the line of sight at about 110 kilometers per second, roughly 250,000 miles per hour. That radial velocity is solid, it comes from the Doppler shift of well-measured spectral lines. You can say the Milky Way and Andromeda are already gravitationally interacting. Their halos overlap in influence, and they are falling together inside the local group's potential. You can say that if a merger does happen, it's not coming soon by any human standard. The first strong interaction is likely more than 4 billion years away, and a complete blended remnant, if it forms, is more like 8 to 10 billion years out. You can also say that a merger, if it happens, won't literally destroy the solar system in the sense of tearing planets out of orbit. The main risk to Earth is still the Sun's own evolution, not Andromeda. And you can say that as of 2025, after combining Gaia, Hubble, satellite galaxies and big simulations, the best estimate is roughly a 50-50 chance that the Milky Way and Andromeda actually collide and fully merge within the next 10 billion years. Not 99%, not destined, about half. That leads to the real twist, which has nothing to do with special effects and everything to do with process. The dramatic part of this story is not galaxies might collide, it's that one of the most popular confident claims in astronomy, the fixed fate of your entire galaxy, got downgraded by a few micro-arcseconds per year. A sideways drift so small you have to split a degree into 140 million pieces to see it, plus a few tens of kilometers per second in satellite motions, was enough to flip the narrative from "we know" to "we're not sure." You watched science change its mind in public, first leaning heavily on Hubble's almost radial orbit, then folding in Gaia's long baseline, the pull of the Large Magellanic Cloud, the massive M33 streams and dwarfs, and finally coming out with, actually, it's a coin toss. That isn't a failure. It's exactly how this is supposed to work when the stakes are high and the timescales are ridiculous. So where do you fit into this as someone watching these headlines go by? When you see the next big claim about dark energy changing, or a new map of the cosmic web, or some update about the ultimate fate of the universe, this Andromeda story is your template. Don't treat those headlines as prophecy. Treat them as forecasts that depend on data and models that are still evolving. The first questions you should have in your head are, What new measurements went into this? What changed compared to last time? How big are the error bars? The real drama isn't in the picture of colliding galaxies, it's in those tiny updates to velocities, distances, and masses that force people to rewrite confident stories. That's the point of ending on Andromeda. It's not to scare you with a doom date, it's to show you that even something as grand as the fate of the Milky Way is conditional. It hangs on micro-arcseconds, on halo profiles, on satellites we're still weighing, on missions that are still downloading data. You don't live in a universe with a scripted end, you live in a universe where even galaxies have uncertain futures. The Andromeda collision was once a fixed date on the cosmic calendar. Now it's a question, and the answer depends on the next few micro-arcseconds. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.